All right, here I'm going to talk you through how I would recommend you go about studying for this, reading this chapter on climate and meteorology and kind of all the parts that we're moving into. So here goes. So I'm taking a look here at Unit 6. This is Chapter 16 called Atmosphere, Composition, Structure, and Temperature. And what we have here, this is just a picture of an object that's actually located at a very high elevation. And you can find this on page 445 of your textbook, just looking down here. And it's starting us off with recognizing the difference between weather and climate. Now, when I read through the material, I like to think of, the bold-faced terms, obviously. I'm not teaching you how to read, but I do want to highlight a couple things. So I want to make sure that we're going to jump right in here to weather. Weather is constantly changing, sometimes from hour to hour, and other times from day to day. It's a term that refers to the state of the atmosphere at a given time and place, whereas changes in weather are continuous and sometimes seemingly erratic. It is nevertheless possible to arrive at a generalization of these variations. Such a description of aggregate weather condition is called climate. It is based on observations that have accumulated over many years. Climate is often simply put as average weather. But this is an inadequate definition. So we're going to be making sure that when you look out the window, I think a good way of looking at it would be when you look out the window, you see weather. Weather over the course of, say, 100 years would be a climate. So we've got climate as a longer time duration where weather itself, right? Climate is a longer term duration where weather is an immediate, right? I can observe weather. I'm not really observing climate. So here I've got a couple different pictures that just depict, let's just say, different scenarios playing out here. Here I have post-hurricane. Here I have a snowstorm. And here I have landslides from extreme rain and tremendous flooding. Here I've got different severe air pollution. This is just a smog-induced pollution that's taking place here on page 447. Here I'm going to start looking at different graphs that are showing temperatures. Notice that we've got these three different plotted points here. But I always say, a lot of times when I read, I overlook the pictures and the graphs. And really the pictures and the graphs are helping me make sense of the reading material. So this is a graph showing daily temperature data for New York City. In addition to the average daily maximum and minimum temperatures for each month, extremes are also shown. As this graph shows, there can be significant departures from average. So averages, you can have extreme highs and extreme lows, as we've got these different colors here showing just that. Composition of the atmosphere. Now we'll study this a little bit further, and we're not going to get into the sources of pollution on this page here. That's not exactly where we're at right here, right now. It's not the scope and scale. But I will say that this picture here on page 450, this shouldn't be this most complex topic. We should realize that about roughly 78% of our total atmosphere is composed of nitrogen, and about 21% is that of oxygen. That 99% of our atmospheric gases are composed of nitrogen predominantly and oxygen. And then we've got these trace gases here. We have argon that kind of fits in next at about 1%, or 0.9% to be precise. And then carbon dioxide, and then all kinds of trace gases that are located in here. So our atmosphere. So there are what are called variable components. We've got water vapor, tiny amounts of water vapor, what we would say about up to 4% by volume. This is what creates clouds. So we can't ignore that small components, these variable components, are significant. We have aerosols. Aerosols are these dust particles that get trapped and transferred within the atmosphere itself. We can talk ozone. Ozone is this O3 molecule. It's a nice blanket for ultraviolet light. It's a shield. It's a shielding technique. Ultraviolet light is a very damaging set of electromagnetic spectrum, right? Photons, energy, pure energy, that do damage to life. So we've got these variable components that we're looking at here. Here's a picture. These are dust storms. These are dust storms that are kicking up all these different aerosols, and these literally scatter themselves as fine particulates travel throughout the atmosphere, and they travel around the planet. And then as a result of that, in this picture here, it shows that we actually can get these reddish sunsets and that just is the elongation. And we'll talk about why we have red sunsets anyway. But those dust particulates further scatter sunlight, so the setting sun would actually be a little bit even more red. Now, we're not going to do a lot of reading but on ozone. I don't talk a lot of ozone, but really this is the ozone depletion hole, and I think it's an interesting read on page 452. But when we talk about height and structure of our atmosphere, we're going to have to make sure we pay attention to how pressure changes. As I move up in elevation, it's got less air above me, so there's a lower pressure, right? So pressure changes. The temperature changes. As I rise vertically in elevation or altitude, I will be getting cooler. We can talk about the thermal gradient, the temperature differential as I rise vertically. Then it gets colder or gets cooler. Now, this is a picture on this page right here. We're talking about the different layers of atmosphere, and I'm simply just going to jump right into this graph or this picture here. And this is a picture we have looked at in class, and this is a part of our lecture that I'm going to go over one more time. The troposphere is very significant to us. It's significant because this is where we live. That our atmosphere heats from the ground up. We have these short wave that we call visible light coming and hitting the Earth's surface. Roughly 50% of it is absorbed, and some of that is re-emitted back into the space above it. As that parcel of air rises, it cools. It cools up as it goes from the troposphere into the stratosphere, and this is what is referred to as the tropopause. It's simply a layer that differentiates the troposphere into the stratosphere. And in the stratosphere is this layer of ozone, ozone being the O3 molecule that shields the Earth from dangerous ultraviolet light. So moving on here, we've already studied and looked at the Earth-Sun relationships here, right? We've studied this. We've already gone over this, but let's make sure we realize Earth has two different motions. It's both rotating and it is also revolving around the sun. And the revolution around the sun at different angle, right, at the axial tilt, allows the sun to be at different elevations or heights in the sky. And during our winter, it's at a lower angle. And in the summer, it's at a higher angle. Here's a picture that we've studied this at an axial tilt, right? This would be, what is this? This would be the Tropic of Capricorn. This would be December 21st. This would be a winter solstice. And here are the positions of the Earth as it's moving through its orbit. And here are mechanisms and modes of heat transfer. And that should pretty much get us through. I guess I've got the electromagnetic spectrum here. I guess I haven't finished that up. I was actually trying to go quicker to beat the bell, so you didn't have to hear that. But you do, so you'll be fine. Here we have the electromagnetic spectrum. Just to make sure that we understand that short waves and long waves. We're comparing the difference between a long wave would be infrared, and a short wave would be that of visible light. Rainbows are kind of a cool scenario. We can actually get a broad range of what the phenomena that take place when I separate out white light into its characteristic components, and we have water droplets can act like a prism, and they can separate it into the Roy G. Biv, the colors that are located within white light itself. Here we have a picture of the fate of incoming solar radiation. If this is solar radiation, roughly 50% finds its way into the Earth's surface, where some of it can be backscattered, right? It can be reflected, and it can be absorbed. So we've got all of the total light and heat budget that can be accounted for, and that's what we refer to as the heat budget. Let's see here. We can talk about reflection and scattering. Photons do different things when they come into contact with different objects. We've identified the term of albedo. It's simply the ability to reflect light, right? Higher albedos reflect light better. Lower albedos, let's just say they absorb a lot better. And here's a nice picture to reiterate that. This picture's on page 464. And so now it takes us to the greenhouse effect. And so there's a lot of information to really truly get an understanding as to what's taking place. We have to understand all of the terminology to make sense to understand how cool and how fascinating the greenhouse effect actually is. So we often study temperature, air temperatures, to determine what's taking place on the planet. So it really comes down to where is the location that we're looking at. So we look at our local 42 degree north latitude, and we pay attention to what's taking place in our local area. That we have this shortwave energy that's absorbed by the Earth's surface. It's re-emitted as long wave, and some of that energy then gets trapped by greenhouse gases. The one that gets the most publicity is carbon dioxide, but we could also add water vapor into that mix and methane. Methane and carbon dioxide are your two primaries that get a lot of the publicity when we talk about greenhouse effect and climate change and global warming. Those are hot button items. Here we have just a different temperature map. These are just different isotherm maps. They just have regions that are located at different temperatures here. So we've got this color-coded map. We've got these different lines here that align similar temperatures. And last but never least, last couple pages, here we know that land and water heat up differently. They have different specific heats. And because they have different specific heats, we have, really we can look at this as they have not only different, they're going to heat up differently, but they're also going to emit heat differently. Land is going to heat up a lot quicker, and it's going to re-emit a lot more heat, and that's why we have a much redder sequence of land here. And this is in California and into Nevada. And let's see, altitude, as we rise up vertically, air cools a lot quicker. The geographic position means a lot, right? Closer to the equator is going to have a lot more direct incoming solar radiation, right? Insolation is a primary feature here. Let's see, cloud cover and albedo. Different locations have a greater tendency to having clouds. Clouds are going to reflect light. If it's located near a coast, coastal cities are going to be more influenced by bodies of water, ocean currents. World distributions of temperature are going to vary, right? So there's a lot of factors that influence what a local area is going to be experiencing in terms of temperature. And these isotherms are going to kind of show us that in January, the isotherms, the warmer temperature is going to be located in the southern hemisphere here, right? And hopefully that's an obvious depiction of what's taking place here, right? Land is going to be warmer than that of the water. And the sun in January is going to be located in the southern hemisphere. Where in the northern hemisphere, in July, the northern hemisphere is going to be receiving the greatest sunlight energy. So here these are just showing me what we have with the hottest locations are going to be on land, located directly beneath where the sun is coming into most direct angle, or closest to 90 degrees. And then last but not least, there's a lot of good information, a lot of good terminology that you can go through on page 473 and into page 474. And I expect you to be able to answer the questions on page 474. And I want you to go ahead and answer questions 1 through 23. It seems like a lot. I think you'll benefit from that. There you go.